Good morning. This is a very short video on how to actually calculate a standard delta G. And I have a lot of the math done here, so if you're following along in your notes, you can pause and take a look. But again, delta G, this little circle means prime, is the total net loss of energy or gain of energy of a reaction. So if we have a reaction that's going from reactants to products, if I could simply add up all the energy reactants and all the energy of the products and just subtract the two, then that's what I want to find out. That's because of the first law of conservation of energy, that tells me my difference in energy. So this is what we call a state function, and anything where you just want to, your difference from your start to end is a state function. That would be the change is equal to the sum of all the products minus the sum of all the reactants, and they're all calculated the same way, whether it's delta G, with delta H, or delta S. Again, I've highlighted how to calculate delta H off your charts, delta S off your charts, and now I'll do a third example, although albeit it is exactly the same. Okay. Now delta G, again, measuring total energy is difficult. So we are going to do a delta G of formation. So the equation here, now I'll rewrite it here, is delta G prime of your reaction is equal to the sum of the delta G of formation of your products minus the sum of the delta G of formation of your reactants. So that is the equation, which is your state function. So I have done an equation here, which is methanol, and I balanced it, 2 methanols plus 3 oxygens. I do believe this is saying it is a gas, and then forming 2 carbon dioxides, and then 4 waters, also gases. Again, this thing will have a delta H, which will be negative because all combustion reactions are quite exothermic. And then delta S will be positive because I have, I have 5 gas particles here going to 6 gas particles, so I'm increasing the amount of movement I have. So like many combustion reactions, also we are increasing in entropy. So there's a certain amount of energy involved with this. So I'm going to go pretty quickly here. Now, again, in this equation, there's 2 deltas. There's a first delta, which is your difference between your elements and your actual chemicals involved. So I have carbon, hydrogen, and oxygen, and how much energy does it take to get from these elements to the individuals in question. That's my common measuring stick. So negative 161 is my delta G of formation. That's this delta right here. Of course, elements in that case therefore are 0 because it takes no energy to go from an element to an element. So I have gone off my charts and I have gathered all the information. This is where bookkeeping pays dividends, because there's a lot of numbers, and if you're being sloppy, you can get numbers mixed up. You can just make clerical errors because we're human. So do it the same way every time. Be as careful as you can. All right. So in this case, we have 2 of these guys. This is the amount energy it takes for 1 mole of carbon, hydrogen, oxygen to make 1 mole of this. So since we have 2 of them, we multiply this times 2, which gives you 322 negative. This is still times 0, and then multiply times 2 here, times 4 here. Gives me negative 912, negative 78, which is a negative 1700, and then negative 322. Take your products minus your reactants is negative 1700 minus a negative 322 equals a negative 1378. That means every time this thing cycles through, I get 1378 energy, kilojoules of energy. Now that's not all in the form of heat. Some of it is tied up in producing disorder, but in this case, 2 moles of this, 3 moles of this, 2 moles of this, and 4 moles of this gives you, negative 1378 kilojoules of energy. In this case, of course, we've already detailed this equation, how to calculate delta G. You can use your charts, okay, to get this. An alternate way is you could use this equation, delta H prime minus temperature delta H delta S prime. You could use your charts to figure out, it's a longer way, but you could chart to figure it out here. You chart to figure out your delta H, plug in 298 for your temperature, and you could solve for your delta G. This should give you the same delta G that you have here. If you want to alter your temperature, well then you're no longer at STP. STP means we're starting at 25 degrees Celsius, so if you change that temperature outside of the 298 Kelvin, which is the same as 25 degrees Celsius, then that's fine. You'll get a new delta G, and that's quite common, but there is some inherent error because these are both still being measured at 298, but that generally is how they do it. Okay. So how to calculate delta G using a state function, pretty straightforward. Thank you.